In this video, we're going to talk about case 3 for evaluating a limit algebraically, and that's if we end up with what's called an indeterminate form. So before we get into that, there is something I wanted to end the last video with, and I want to go back and do that right now. So let's remind ourselves, in the last video, in example A, we were evaluating the limit as x approaches 2 of this function, x squared over 2 minus x. And we did it algebraically. We showed that from one side, from the right side, the limit was negative infinity, and from the left side, the limit was positive infinity. So overall, that meant that the limit does not exist. So let's just check using the graph that matches up with what the graph says. Okay, so this is Desmos, and I've graphed our function here, and I see part of the graph here. So as x is getting close to 2 from the left-hand side, the y values do tend to get really, really large. But oh no, that's not what I want to do. I want to drag the graph, and I want to zoom out a little bit so we can see what's happening on the other side of 2. So on the other side of 2, it looks like, yeah, as we approach 2, which is here, from the right, the y values do go to negative infinity. And that's what we got with the algebra. Okay. So when we evaluate limits like this, unless a problem specifically says, do it using the graph, or do it numerically using a table of values, I want you to do it algebraically. So in a problem like this, I really would be looking for work like what we did here, plugging in, finding what strategy to use, and then applying that strategy. So if you were to just do this problem and just tell me the final answer, by referring to the graph when that wasn't the intention, you would likely get very little credit. So that's something to keep in mind. I want you to understand these arguments about how we figure it out algebraically. Okay, so now let's go back into this actual video, which is talking about what are indeterminate forms. So we want to evaluate a limit, the limit as x approaches a of f of x. So we always begin by plugging in. So let's say that we plug in and we get something like 0 over 0 or infinity over infinity, and maybe some of these infinities might be negative. So let me say plus or minus infinity over plus or minus infinity, or infinity minus infinity, or 0 times infinity. And when I write infinity here, I mean, let's just say that when we plug in, we end up with something really, really large, something that's getting infinitely large. And there are a few more. There are 3 other ones that I'm going to write down, but the last 3 we'll see much less until later in the course. So one is infinity to the 0 power, one is 1 to the infinity power, and one is 0 to the 0 power. So all of these things are called indeterminate forms. Indeterminate forms. And what indeterminate forms are is they are limits. They're sort of what we get when we plug into a limit that can't be determined just by looking at them. So if you know something has the form 0 over 0, but nothing else, we don't know what it is. An indeterminate form could theoretically be anything, depending on the scenario. It could be does not exist. It could be a number, a finite number. It could also be infinite. We can't tell. We can't determine them. That's why they're called indeterminate. Indeterminate literally means it cannot be determined. So if we plug in and we get one of these indeterminate forms, we must simplify first. Okay, so case 3 is the case that typically shows up most often. Okay, so for this case, we have to simplify first. So let's look at an example. So let's say I have the limit as x approaches 2 of x cubed minus 8 over x minus 2. So we actually saw this limit back in section 3.1 when we were doing things with a table of values. But let's see if we can do this algebraically now. So let's plug in, because that's our first step when we do things algebraically. And that gives us 2 cubed on top, minus 8, over on the bottom, 2 minus 2. So the top is 0, and the bottom is 0. And that is one of our indeterminate forms. And when we have an indeterminate form, we need to simplify. Okay, so how do we simplify something like this? And this is where I want to do a brief review of some factoring formulas from algebra. So the first is the difference of cubes, and that says a cubed minus b cubed. So it's a difference because we're subtracting two things. And it's cubes because the things that we're subtracting are cubes, something cubed and then something cubed. So a cubed minus b cubed factors as a minus b times a squared plus ab plus b squared. And the sum of cubes has a really similar factorization. Okay, just a couple of the signs are different. So notice that this minus b changed to a plus b, and then the sign in the middle of this plus ab term changed to the minus ab. In fact, there's a quick way to get the second formula from the first. And the quick way to do it is you just replace b with negative b. If you did that, the minus b cubed would end up becoming negative b cubed, which ends up being plus b cubed. So that'll give us the sum of cubes. And if you replace the b with negative b on the right hand side, it'll switch exactly those two signs. All right, so is there one of these formulas that applies for our problem, either a difference of cubes or sum of cubes? Pause the video for 30 seconds and see if you can identify which one applies. 4, 3, 2, 1, pause the video. Pause the video and see if you can determine, is it difference of cubes that we can use or sum of cubes? And if you figure out which one, then go ahead and try to use it to factor this. All right, so hopefully you've done that. Hopefully you've paused the video for at least 30 seconds to think about this. Okay, so we have the limit as x approaches 2, and the numerator is, I got something cubed first, something cubed second, and the minus sign is what indicates to me it's going to be a difference of cubes. So I'm deliberately leaving myself with just some blank parentheses so I can really review and show you how these steps work for factoring something with a difference of cubes or sum of cubes. All right, so we have the limit as x approaches 2, denominator is x minus 2. On the numerator, well, what cubed is going to be x cubed? Well, it's x. X, when you cube it, is x to the third. And then what goes in the second parentheses? What, when I cube it, ends up giving me 8? And the answer is 2. 2 cubed is 8. All right, so now we have something cubed minus something cubed on the top, so we can use a difference of cubes. So we got limit as x approaches 2. So it's like in my numerator here, it's kind of like my a in the difference of cubes formula, I'm replacing it with x. And the b is being replaced with 2. So when we do that, the numerator will end up being, so instead of a minus b, it'll be x minus 2, and then a squared would end up being x squared plus ab, so x times 2, plus b squared, which is 2 squared. So that's my difference of cubes, and on the denominator, we have x minus 2. So the nice thing is, now the x minus 2's cancel. So when we do that, we get the limit as x approaches 2 of x squared plus 2x plus 4. All right. And now that that x minus 2 has canceled, notice that the thing that was sort of preventing us from plugging in before is gone. Because when we plugged in 2 before, the denominator was 0, and that was the problem. Now that problem has canceled away, so at this point we are good to plug in. So we are good now to plug in And plugging in, we get 2 squared plus 2 times 2 plus 4, and that is 12. And that's our limit. If you compare this to what we got using our table of values back in section 3.1, we actually got the same thing. So one important note that I want to make about this is when we've canceled something on the top and the bottom of a fraction before, we've included a domain restriction in what we've written. So with this problem though, now that we have a limit, we actually don't need to worry about that, but it's important for me to talk about why. So when it says that x is approaching 2, that means x is close to 2, but not equal to 2, but not equal. In fact, let me just keep that in green. I like it better like that, I think. But not equal to 2. So we don't need to worry about the domain restriction that x is not equal to 2. So it's important not to forget about that domain restriction altogether, but in the context of this problem, what this technically means when we have this limit as x approaches 2 is we're not actually plugging 2 in. We're not asking ourselves what's happening with the function when we plug 2 in. We're asking ourselves what's happening with the function as we plug in something that's really, really close to 2. Even over here, when we plugged in 2, that was just a technique that lets us arrive at the correct answer. But actually what we're answering when we say this is 12 is, what's the value, what's the y value that this approaches, x squared plus 2x plus 4 approaches, as x gets really, really close to 2. And it just so happens to be the same thing that we get if we just plug 2 in straight up. But we weren't able to plug 2 in straight up into the previous fraction. And even after we did simplify, although we did plug in 2 sort of straight up, technically what that sort of answers for us is just what's happening to our function as x gets really, really close to 2. So it doesn't violate our domain restriction, and that is very key. All right, so one important notational thing about problems like this, or just general limit problems, is when we have a limit problem and we're simplifying, we need to keep writing the limit until we plug in. So this problem, there were several steps where we wrote the limit in front. The limit in front was written here in the first step. It was written here, written here, written here, written here. Only when we plugged in, and the plug-in happened here, did we stop writing that limit. And that is really important. The meaning of our expression changes when we don't have that limit in front. When we don't have that limit in front, it's just a function. When we have the limit in front, it means, well, what is the function approaching as x gets really, really close to some number? All right, so let's do one more example. So suppose we want to evaluate the limit as x approaches 4 of negative 3x plus 12 over x minus 4 cubed. So the first thing that we want to do is plug in. And if we plug into this, we end up getting negative 3 times 4 plus 12 on the top. On the bottom, we'll end up with 4 minus 4 cubed, which gives us 0 over 0. So this is definitely an indeterminate form. Indeterminate form. And again, it's of the form 0 over 0, just like in the previous example. So we need to simplify. Okay, so let's simplify this. And again, I need to keep writing that limit in front until I'm actually legally able to plug in. Okay, so on the top, we can factor out it'll actually be best to factor out a negative 3, because if I do that, I'm left with x minus 4. and then on the denominator I get x minus 4 cubed. And now I can cancel out 1x minus 4 and get the limit as x approaches 4 of, we got negative 3 on the top. On the bottom we have x minus 4 squared. Alright, so let's continue this. Alright, so I moved this up to the top of the page to give myself some more room. But now let's plug in again. We've canceled a little bit. Let's try plugging in one more time. So when we plug in again, we get negative 3 over 0. Okay, so we got negative 3 over 0. So we have a non-zero on top, 0 on the bottom. And that means we're in case 2 now. So now we got to take one-sided limits. So we started off with an indeterminate form. We simplified a little bit, and now we have a non-zero over 0, so we ended up in case 2 within case 3. So let's take some one-sided limits. So let's do the limit from the left and the limit from the right. So limit as x approaches 4 from the left of negative 3 over x minus 4 squared. So when we plug in, we'll have the negative and the 3 here. On the bottom, I know I'll have some type of 0. I just don't know if it's 0 with a negative sign or 0 with a positive sign. And with this problem, there's a shortcut for determining what it is. Because x minus 4 squared is always non-negative due to the even power. Which means on the bottom, we will have 0 with a plus sign. In fact, we'll have that no matter which direction we're approaching from. So even if we take the limit as x approaches 4 from the right of negative 3 over x minus 4 squared, we'll still have the minus 3, but the denominator now is going to be 0 with should be a plus still, plus sign, because the denominator is always non-negative. Okay, so now let's simplify these. So I know it's going to be some type of infinity when we have a non-zero over 0. Overall, this is going to end up being a negative number. Because 3 is positive, the denominator is positive, but the negative in front makes it negative. That's why it's negative infinity. And same thing with the one below, because it's exactly the same, negative infinity. So those two one-sided limits are the same. Therefore, we get to say that the limit as x approaches 4 of negative 3 over x minus 4, x minus 4 squared is negative infinity. And if you're saying, wait, isn't that d and e? You'd be right, it is d and e. But remember, if a limit falls into the d and e category because it's infinite, if it is infinity or negative infinity from both sides, if we're talking about a two-sided limit, we need to specify that. We need to specify whether it's infinity or negative infinity. So we need to write the answer like this. Okay, so the key thing that I want to now notice about this is, notice that in this second example, we had a 0 over 0 limit that ended up being some type of infinity. It was negative infinity. So that can happen. Indeterminate form can be negative infinity. And in the first example that we did, we had 0 over 0, an indeterminate form. And that indeterminate form ended up being a finite number. And that's part of what makes indeterminate forms indeterminate. Just by looking at the fact that something is 0 over 0, I don't know if it's going to be a finite number. It could be. I don't know if it's going to be infinite. It could be. We've seen examples of both. We have to simplify first to figure it out. All right, so in terms of our goals, we have now talked about the third case for evaluating limits algebraically, which is, what do we do when we have an indeterminate form?